Hello, this is a special presentation from Mr. Sadler to correspond with Lecture Exam 1, and also it's kind of an intermediate between Chapter 1 and Chapter 2, which is the Introduction and Minerals. This is Relative and Absolute Age Dating, and I wanted to kind of break it out into its own thing because it's pretty complicated as we go along, as you'll see. So we'll begin with the drawing of an atom. This atom has 6 protons and 6 neutrons, and surrounding it, it has 6 electrons. Now, for those chemistry buffs out there, of course, 2 electrons occupy the first shell or orbit, and a maximum of 8 can occupy the second orbit. But just to simplify my picture, I just show the electrons as a single orbit. So because it has 6 protons, if you look that up on the periodic table of elements, it is a carbon atom. That is its identity. And therefore, that is the atomic number is going to be the number of protons, which is 6. Now, when you consider the atomic mass number, or the number of protons and neutrons, if you count them, obviously, you get 12. So, therefore, this is called a carbon-12 atom. So now what I'm going to do in this slide is that I have 2 atoms that are side by side with one another with only one difference, and you can probably spot the difference. This is a carbon-12 atom, which is written as C12, but over here we have carbon-13, which is written as C13, and of course carbon-13 being the atomic mass number. So same type of deal, but I'm now expanding on this discussion. So again, we have 2 carbon atoms, carbon-12 on the left and carbon-13 on the right. Because they're both carbon and because they have the same number of protons but different numbers of neutrons, that is what makes them isotopes of one another. So an isotope is 2 atoms that have the same number of proton but different numbers of neutrons. So let me talk a little bit about what isotopes are. And it's exactly how I explained it. 2 atoms, both having the same number of protons, but having a different number of neutrons, which really makes the one that has more neutrons heavier, because neutrons do not have an electrical charge. Of course, protons are positively charged, and electrons are negatively charged. So again, we're going to kind of do the same thing with protons, neutrons, and electrons. 2 carbon atoms, 2 isotopes of carbon, carbon-12 and carbon-13. Now, the one atom that has different numbers of protons than neutrons in its own atom is going to be the one shown on the right, this one. So because he has different numbers of neutrons than protons in his nucleus, that is what is probably going to make him radioactive. So this is a radioactive isotope of carbon, or also known as a radioisotope. So what does it mean to be radioactive? Okay, well, first of all, it means that it's going to be unstable. So an element that is radioactive is physically going to change into something else over the course of its life. And how it changes is it actually gives off radioactive particles in the form of radiation. Now, to think of it in terms of the atom, sometimes a radioactive particle will be 2 protons and 2 neutrons. So when 2 protons and 2 neutrons fly off from the nucleus, for example in carbon-12, if you go messing around and pulling out protons, it's no longer carbon. It's physically going to change into something else. So that's what I say here. You're actually changing into something else, or changing its identity. In fact, that you're changing into something brand new. And eventually, the ultimate change for one radioactive element into another element, it's going to form a stable element. So, for example, carbon-12 will eventually turn into nitrogen, and nitrogen in this context is known as a daughter product. So whatever stable outcome it is from the radioactivity, that's called the daughter product. So let's do a quick little example before we proceed with more geological type stuff. Carbon-14 is a new isotope of carbon we haven't considered. So how many protons does carbon atom have? Of course, it's got 6. How many neutrons? Well, carbon-14 is an isotope of carbon, so it has to have 6 to be carbon, and it's going to have 8 if it's got to be carbon-14. So 6 protons and 8 neutrons. So carbon-14, over the course of its life, some of it will turn into nitrogen-14, which is called the daughter product. And that's where half-life comes in. Half-life is the time it takes for half of a given substance to physically change into the daughter product, or to decay, radioactively decay, to the daughter. So for example, in terms of carbon-14, it'll turn eventually into nitrogen-14. But only half of it is turning into the daughter at a time, after every single half-life that goes by. So here's an example of radioactive decay. Okay, the half-life of carbon-14 is 5,730 years. So what that means is if you have a solid block of carbon-14, in 5,730 years, half of that block will radioactively decay to nitrogen-14, and the other half will still be carbon-14. Okay, so I'm going to demonstrate this right here. So here's time 0, time beginning, when it formed out of the earth, 100% parent. Okay, so let's say that we're going to decay this through one half-life. This is carbon-14. So 5,730 years has elapsed. So what will happen is that this half right here that I'm shading in, this half has already turned into the daughter product of nitrogen-14. Okay, so what is remaining is half of the original parent. So what will happen over another half-life is that half of that parent, whatever is remaining, will alter to nitrogen-14. And therefore, if you consider the whole block from time 0, 3/4 of the original parent have now decayed through 2 half-lives, and 1/4 of the original parent is remaining. So here is a beautiful little picture to show or illustrate that. For each half-life, let's see, what is it? For each half-life, taking half of the remaining parent. Okay, so you see that where it says a number of half-lives at the bottom, okay, if you look up, you notice that half of the original parent is still there. You go to 2 half-lives, and 1/4 of the original parent is still there. 3 half-lives, 1/8 of the original parent is still there, and so forth. So through taking radioactive decay, or anything that's radioactive, you really don't ever get rid of all the parent. So this is really the premise of absolute age dating, or radioactive dating, or radiometric dating, or however you want to say it. So absolute age dating works by, number 1, knowing which radioactive isotope is in your sample. So is it carbon-14, is it uranium-235, which all have different half-life numbers. Another thing you have to know about your sample if you're going to do absolute age dating is you have to know the half-life of your particular radioactive isotope. So if you're dealing with Egyptian mummies, for example, all living things, when they die, will begin to, well, first of all living things as they're alive incorporate carbon-14 into their bodies. So that the instance that the second that we die, the carbon-14 begins to radioactively decay to nitrogen-14. So this is how Egyptian mummies are age dated. Another thing you have to know if you're dealing with absolute age of rocks is how much parent is in your sample and how much daughter is in your sample. Then you can basically take it back through the half-lives to time 0, and you can determine the age in which it formed. Okay, so all that discussion was about absolute age dating. Now we're going to get into relative age dating, which is a little bit different ball game, and I think a little bit easier. So when a geologist uses relative age dating, they're determining the sequence of events of your geologic rock formations without specifically knowing the age of the rock formations themselves. And this is a really fast and really handy tool when you're out there in the field looking at rock layers and strata. Okay, so let me just kind of go through these different deals here. There are specific laws of geology that help guide us when determining the relative age of rock layers. Determining relative ages. So these very specific laws, they were developed by a particular fellow by the name of Nicholas Steno. And I believe he was an early geology type person. And again, relative age dating is used in the discipline of geology, which is known as stratigraphy. And anything that is stratigraphic or stratigraphy related deals with the layering or the strata of sedimentary rock units. So basically, stratigraphy is a study of sedimentary rocks and their layering, which is what these laws are going to apply to. So here we go. This is the first law of geology, of stratigraphy, which is called the law of superposition. And the law of superposition basically says that in a layered sequence, the oldest rock formation is sitting on the bottom, and the youngest rock formation is on the top. And of course, a big assumption is here. The assumption is that the rocks layers were not flipped over. Okay, so there's usually going to be some evidence of that, but you have to scratch around for that. So let's look at how this is demonstrated in the real world. So we have rock layers D, E, F, and G. So based on the law of superposition, can you tell me which one is the oldest? And of course the answer is rock layer D because it's sitting on the bottom. The second law of geology, or the law of stratigraphy, is called the law of original horizontality. Originally horizontal. So this says that sedimentary rocks, when they were originally deposited underwater, were originally deposited flat or in horizontal layers. Because when sediment comes to rest at the bottom of a lake, or sometimes in the bottom of a stream, or definitely in the bottom of an ocean, they are deposited in flat layers, just like I drew on the previous slide when I drew layers D, E, and whatever. Now, this is a kind of unusual setup in this picture because the big question is with layers G through L. Okay, it says, is this how these layers were formed originally, were first laid down or deposited? Is this how they were originally deposited? The answer is no. Okay, so how did this actually come about? So you began, or the earth or a stream or a lake or whatever, began to accumulate sediments in one layer after the other, G, H, I, K, and L. I don't know why I skipped J. Okay, then what happened is that something came along and tilted the rock layers and made them go on their side. So they were tilted. May have been tectonic forces or mountain building episodes, something like that. And then the next thing that happened is you still have the same layers here, but you have erosion at the top, which basically cut off all the tops of the layers. So this is a specific type of thing which we'll talk about here in a minute. The third law of geology is called the law of lateral continuity, and this is one of my favorites, and I see it all the time when I go driving around America. So I'm going to take you now to a very special place in Arizona, which has a layer of limestone and a layer of sandstone. So what I've written here, it says, welcome to the Grand Canyon. So when you're standing on one side of the Grand Canyon, you're standing on a sandstone. And when you look across to the other side of the canyon, and maybe you're waving to your friend, they are probably also standing on the same sandstone because the layers of the Grand Canyon are flat. Okay, unlike how I've kind of drawn them here. So what the law of lateral continuity says is that the canyon is now, so the canyon is now formed in the Grand Canyon, of course. But at one time, there was no canyon because the river didn't cut down. So at one time, these layers were actually laterally continuous. They were one big layer that was eventually cut down by the river. So this is a beautiful cross-cutting relationship problem because you can tell that the layers had to be there first in order for the river to cut down through them. So if I were to ask you which is younger, the river or the rock layers, you would say that the river is younger than the rock layers. The fourth law of geology is called the law of fossil succession. And I find this one kind of cheesy in a way. It's really not much to it. So I'm going to give it to you in a nutshell. So if you consider some rocks and you're out there looking in sedimentary rocks and you found a fossil at the bottom and it looks like a horn coral, and then the one at the top maybe is a starfish. If you know the genus and species of that horn coral, and if you know the genus and species of that starfish, then therefore you can probably determine the relative age or even the absolute age of those rock layers that they're entombed in. And this is especially helpful if the horn coral and or the starfish, and of course many other fossils, only lived a certain amount of time in the geologic record, if they have a very short geologic range. So that tells you that it's only Cambrian rocks at their end, or Ordovician rocks, or so forth. The fifth and final law of geology is one of my favorites, and this is the law of cross-cutting relationships. And this one's fairly straightforward to understand. This one really, in a nutshell, says that whatever geologic feature is doing the cutting across other things is younger than what is actually being cut. Okay, so you're going to see a real-life picture, I think, here in a second. Okay, maybe after this one. So I'm going to draw some stuff here. We have layers C, B, and A. Then there's a fault. And then there is erosion. And then we have layers X and Y deposited on top of everything. So the ultimate question when it comes to this picture is, when you look at the fault, which is younger? It says that younger or older than A. So is the fault younger or older than layer A? And of course you realize that layers C, B, and A were first deposited flat, and then the fault came along and cut across A, and of course B and C. So the fault is younger than A because A had to be there in order for it to be cut. So here's a real-life picture from Maine, and this is called a dike. It started its life as an igneous rock. It was liquid. And the white stuff is conglomerate, so it was just sitting there. And the dike was formed when magma came up into a crack and basically deposited that liquid well, this diabase, as it's called, deposited the diabase inside of it. So the question that's posed is, which is younger? Is it the dike or the conglomerate? And of course the dike is doing the cutting, so he is younger than the conglomerate. So in our final topic in this special segment, okay, these are the 5 laws of geology. Okay, and they all have one big assumption that we have been operating with or on. And the assumption is that every time I put down layers on this Doceri program here, this presentation, that all the layers represent continuous deposition of sediment. So one layer on top of the other. But in real life, that doesn't necessarily have to happen that way. Okay, when I drew layers A, B, C, and D, you're assuming that there are no pauses in deposition. It's just one right on top of the other. Okay, so, but actually you can get pauses in the depositional environment because of changes in things in geology. So when you do have a pause, or what's called a hiatus, you actually form a feature which is called an unconformity. Okay, anytime you have an unconformity, you're going to have missing time. Okay, so let's take a look at the different types of unconformities that are out there in the world. The first one is known as a nonconformity. In a nonconformity, you're going to have igneous rock and or metamorphic rock lying below sedimentary rock. So here's a cheesy little picture to show that. Here is igneous or metamorphic rock below, and you have sedimentary rock above. This assumes that the igneous and metamorphic rock is so hard that through weathering and erosion, it's going to get beat down, it's going to get worn down, and then sedimentary rocks are going to be deposited on top of that. So, in other words, you're going to have some time that's missing. You're going to have some parts of that igneous or metamorphic rock that's going to be scraped off. The second type of unconformity is called an angular unconformity, and this is one that I've already drawn in a previous segment of this Doceri program. So there is an angular unconformity. This is when rocks below are at an angle to the ones above. Number 3 is called a disconformity. And in a disconformity, you're going to have a clear erosional surface in between two sets of flat sedimentary rocks. And that means that you could have a complete whole layer missing, like maybe you scraped off the icing of the cake, and then you put more cake on top of it. So you could have an entire layer missing or many layers missing. The fourth and final type of unconformity is known as a paraconformity. And with this very unique type of unconformity, you do not have a clear erosional surface. So in that middle line, that could actually be an unconformity, but what's separating that second layer from that third layer, you could potentially have 25 million years of rock missing. And missing means either never deposited or it was actually deposited and then sea levels dropped and it was exposed to the elements and it got eroded away. And that concludes the end of our very special segment of relative and absolute age dating.